Hello everyone, welcome back to my channel. In our today's video, we'll be taking a very important topic in chemistry, which help us to determine the structure of various molecules. And that is nothing but the VSEPR theory. It's a basic theory which help us in determination of various structures, the geometry, the shapes, whatever we call it, of the various molecules. Okay. So in our today's video, we'll be trying to first learn what is the basic theory, what is the basic concept of VSEPR theory. Once we learn this concept, then we'll try to learn various tricks to find out the structure of various molecules or ions. Not only that, in our today's video, we'll try to find out that how does the structure is related with the hybridization and how with the help of VSEPR theory itself, you can find out the hybridization in a very easy and convenient way. And we will try to make it in such a way that it will be very fast, accurate, and you can find out the structure in a matter of seconds or minutes. So how to do it? How does VSEPR theory help us to get this structure? And what are the various tricks in finding out the structure or the shape or the geometry of molecules? So let us start with the VSEPR theory. Now, what is VSEPR? As you can see in the screen, it is nothing but valence shell electron pair repulsion theory. So you have various terms. First, valence shell. The outermost shell of an atom is known as valence shell, right? All of us know that. Electron pair. Now, this electron pair, okay, as we know from our basic concept of bonding or covalent bond, remember that whenever a covalent bond is formed, let us try to take one example of covalent bond, like the formation of chlorine molecule. Like chlorine has 7 valence electrons, which I can write in this way, right? So chlorine need one more electron to form or to get the octet. So let's say if there is one more chlorine, okay, which also has 7 valence electron. So what they do is they share this particular one electron. As a result, now both of them will have 8. So this mutual sharing of electron, that is what we call as a covalent bond, results into a sigma bond or a single bond. This particular electron pair, okay, electron pair, which is shared between the two atoms, is known as the bond pair or the shared pair of electron. So what is a bond pair? A bond pair of electron is nothing but the valence electron, which takes part in bonding. That is one. Next, can you see this 3 pairs of electron in chlorine? In both the chlorine we have it. So this 3 pair of electron are nothing but valence electron only. But important, they are not taking part in bonding. So the pair of electron, okay, of the valence shell, which is not taking part in bonding, is known as the lone pair of electrons. So you have 2 types of electron pair. We call it lone pair and bond pair. Okay. Now what happens in a particular molecule? In a molecule where you will have this kind of electron pair, whether it is bond pair or lone pair or bond pair, lone pair, or only bond pair. So there are different cases which we'll be trying to solve. When you have these different types of actually electron pairs, or these 2 types of electron pairs in a particular molecule, obviously they are electron pairs and they tend to repel one another. So according to valence shell electron pair repulsion theory, that repulsion word, so where from that repulsion word comes, according to this particular theory, this electron pair tends to repel one another, okay, in an atom. And what an atom does is to keep them away from one another. Okay, it tries to keep it away from one another. Why it tries to keep it away from one another? Because as they go away from one another, maximum distance from actually one another, they tend to repel less. Right? If I want to minimize the repulsion, I have to keep them as far as possible. So remember that this electron pair in an atom is arranged in such a way that they actually have minimum repulsion with each other. As a result, the system tends to become more stable. So that particular structure which have this lone pair or bond pair in a particular atom, okay, as far as possible from one another, makes the system more stable, and hence as a result it makes it very, very stable, okay, and that will be the structure of that particular molecule, okay. And remember that the central atom in a molecule will decide the structure of that particular molecule. So the electronic arrangement which we are talking about of the electron pair, that is bond pair or lone pair, is of the central atom, not of the surrounding atom. Okay, so the surrounding atom, okay, simply participates in bonding, will be arranged according to the electronic repulsion and where the electronic repulsion is minimum, in which angle the electronic repulsion is minimum. Okay, so in that angle, this surrounding atom will be arranged and hence gives you the geometry. So that's the basic approach in valence shell electron pair repulsion theory, or what we call as VSEPR theory. Okay, that is one. The second thing is that remember that the number of electron pairs or the bond pair and the lone pair will decide the geometry. So if you have electron pair 2, then it will have one particular geometry. If it has electron pair 3, it will have another type of geometry. If it will have electron pair 4, it will have different. So depending upon the electron pair, you will have different types of geometries. So that is what I'll be trying to give you. And then we'll be going for the structural determination. And the last one, remember that the repulsion between different electron pair is different. Like if there is 2 bond pair, the repulsion between the 2 bond pair is always minimum. Okay, because this bond pair are sandwiched between the 2 actually atom. As a result, they are not that free in space. Okay, they don't occupy so much space. It is actually attracted by 2 nucleus. Try to understand that. Okay, 2 atoms. But when you talk about a lone pair is present in one particular atom. Okay, it is not attracted by 2 particular nucleus, only by 1. As a result, it occupies more space. Okay, as a result, you can say it is more free than the bond pair, and hence the repulsion which a lone pair actually shows with another lone pair or a bond pair will always be more than bond pair repulsion. So bond pair repulsion will be the least, then it will be lone pair bond pair, and the maximum repulsion will be actually in the lone pair repulsion. And always remember that whenever you have a particular system where there is only bond pair, I'm repeating it, if you have a particular system, a molecule where you have only bond pair, okay, such type of geometry, we called it regular geometry. Okay, and when you will have a particular geometry where there are lone pairs, this lone pair tends to repel more the bond pair. As a result, the bond angle which you expect should be will not be that particular bond angle. The length, the bond length will also be disturbed in some of the cases, usually the bond angle. As a result, it acquires a distorted geometry. Okay, always remember that whenever we talk about geometry, okay, geometry is nothing but the arrangement of the electron cloud, irrespective of whether it is bond pair or lone pair. So whenever anyone says geometry, what do you mean by geometry? It is nothing but the arrangement of the electron cloud, whether it is from the bond pair or the lone pair. But if anyone will tell you what is the shape of the molecule, always be careful. The shape of a particular molecule is decided by the bond pairs, not by the lone pairs. So for those systems where you have bond pair only, okay, so if you have only bond pair in that particular system, in that particular molecule, then always remember that the geometry and shape is always same. If you have lone pair, then geometry and shape will be 2 different things. Okay, so this basic thing, please remember. If you remember this basic thing, then to get this structure becomes a very easy thing. Okay, so with this basic understanding of VSEPR theory, let us try to go for the structural determination. Okay. So now let us start with some examples. Okay. Now, before going into examples, okay, I'll just give you the structures first. Okay. And then I'll show you how to draw those structures and which molecule will have which structures or which geometries. Okay. So the basic thing which you need to know in VSEPR theory is the number of electron pairs, first of all. So number of electron pairs. Okay. And the another one is geometry. So there are 6 basic geometry which you need to know. The other geometry or the other shapes, sorry, not the geometry, but the shape which you get will be derived from this geometry. And I'll try to show you how. Okay. We'll not try to mug up anything. We'll not try to by heart anything. We'll just try to actually go for this electron pair, which you need to know. Other than that, you don't have to know anything about VSEPR. Okay. All other thing can be derived. Okay. So the first thing is number of electron pair if it is 2. See, when I say electron pair, it can be bond pair, it can be lone pair also. Okay. So I'm not actually saying that it has to be bond pair or it has to be lone pair. But if there are 2 pairs in the central atom, so remember that the geometry is linear. The structure I'll try to show when we go for the application part. If you have 3 electron pair, we call it triangular planar. In some of the textbook, you may get it as trigonal planar. Okay, which will be very much same. When you have 4 electron pair, we call it tetrahedral. Okay. When you have 5 electron pair, we call it triangular bipyramidal or trigonal bipyramidal, which is very much same. Okay. Bipyramidal. Okay. When you have 6, it is known as octahedral. And when you have 7, we call it pentagonal bipyramidal. So these are the 6 basic geometry which you need to know. Okay. So if you know this 6 geometries, you can actually find out anything in VSEPR theory with the help of VSEPR theory. Now, the only thing which we need to know is what is the trick behind, how to get it in a very easy and convenient way. Okay, so let us go for that. So let me just clear this. Okay, so now let us come for the examples. This is the part where you need to focus more. Okay, so how to do or how to get this structure in a very convenient way, very easy way, very fast. Okay, so the basic thing which you need to know is, let us start with a very common example, like let's say methane, CH4. Okay, so if anyone will ask you, let's see, what is the structure of methane, or what is the geometry of methane, what is the shape of methane, what you will do? First of all, always, okay, it is for all generally. First, you will find out the central atom. Obviously, carbon is the central atom over here. You will find out the valence electron on carbon. So valence electron on carbon. Okay, so how many valence electron are there in carbon? Carbon has 4 valence electron. Every one of us know that. Okay, then next is number of bonds. How many number of bonds actually it is forming? So I hope you can understand that hydrogen has a valency of 1, right? So if hydrogen has a valency of 1, that means it will form 4 bonds. So carbon will form 4 bonds. Okay, 4 single bonds. I hope you can understand that we have 4 electrons in carbon and it is forming 4 single bonds. So what will happen? All the valence electron will be used. So if all the valence electron will be used, how many electron is left in the valence electron? 0. So 0 electrons. Okay, so 0 electrons will be left. Now 0 electron means you will have 0 lone pairs. Is it now? Now, so what is the total number of electron pair? So total number of electron pair. So what is the total number of electron pairs we will have? So it is bond pair plus lone pair. BP means bond pair plus lone pair, LP. So how much is how many bond pair? Four bonds, four single bonds, plus how many lone pair? Okay, you will have 0. So 4 plus 0, 4. So how many electron pair you have? 4. Now what I have told you, if it will be 4 electron pair, what is the geometry? Tetrahedron. Now, let's say if you have to draw it, then how will draw it? So first carbon, 4 bondings, 1, 2, slightly longer. Actually, it's not longer, but when you have to draw it, it should be little longer than the others. Then the structure will be little clear. But remember that all the bond lengths and all the angles are same. Then you simply connect it. Then you connect here and you connect this. Okay. And this particular angle which you get in tetrahedral, you have to remember this angle. So the angle which you get is 109 degree to 8 seconds. Okay. So that is nothing but the tetrahedral geometry. Okay. Like for entrance examination, obviously they will ask you which geometry CH4 will have. If, then you just need to know that it's tetrahedral. So if you know that how many electron pair and how many actually, or this particular electron pair gives you what particular geometry, if you know that, then your determination is very, very actually easy. Okay, so that is how actually we need to go for it. Now let us try to take some other examples. Okay, so let us try to take some examples. So the next example which we'll be taking will be, let us take some other structure like PCl5. Very important, right? So let us try to take PCl5. Okay, so the next example, PCl5. So first of all, valence electron on phosphorus. How many? We have 5. Okay, group 15 elements after nitrogen, right? Number of bonds, chlorine, monovalent, so form 5 bonds. 5 minus 5, 0. So 0 lone pair. Okay. Then total number of electron pair, 5 plus 0, which will be 5. So if it is 5, what is the geometry? Triangular bipyramidal or trigonal bipyramidal. So phosphorus, and you simply draw the structure. So triangular, so it is triangular and bipyramidal. Always remember that in phosphorus. Okay, this 5 bonds. Okay, in trigonal bipyramidal geometry, the 3 which you can see, which I am drawing, okay, which forms this triangular plane, okay, or you can say the triangle, okay, obviously, and the bond angle over here will be 120 degree, okay, and this 2 will be known as the axial bonds. Okay, these 3 are equatorial, which are 120 degree to one another, and this 2 is nothing but the 90 degree perpendicular to the plane, and we call it axial bonds. Okay, and always remember that in trigonal bipyramidal geometry, the axial bonds, okay, so these bonds are known as axial bonds. Okay, so these bonds are always longer, okay, compared to the other 3, okay, which we called as equatorials. Okay, these bonds are shorter. Now why it is so? As I've told you, it is because whenever you see over here, it's 90. So these 2 bonds, okay, are 90 degree to the axial plane of the to the axial bonds, and over here they are 120. So obviously this 90 degree is very close compared to 120. So repulsion will be more. So to minimize the repulsion, what they do is the chlorine and the phosphorus, they shift away to minimize the repulsion. As a result, what will happen is resultant repulsion will be less, no doubt, but what will happen is as these 2 atoms are going away from one another, the bond distance, which is nothing but the internuclear distance between phosphorus and chlorine, will be actually higher or longer. Okay, as a result, the 2 axial bonds will always be longer than the 3 equatorial bonds. Okay, it is because of the 90 degree angle. So that is how actually we can get it. So the structure is trigonal bipyramidal. Let us go for the next. Let us try to take some other examples. Okay, so let me take some examples like this. Okay, so NH4 plus ammonium. Okay, let us take a cation. So ammonium ion, how to get this structure? Again, first of all, you need to get the valence electron on nitrogen, right? So how many valence electron on nitrogen? The number of valence electron in nitrogen is 5. Be careful in this kind of cases. See, you have a positive charge. Positive, do you understand? It has lost electron, right? So please deduct the number of electron, or what is the number of positive charge. So over here, the positive charge is 1. So I'm deducting -1. Let's say if there is negative charge, you include 1. Okay. So 5 minus 1, which will be 4. Okay. So once you are done with that, then the next thing which you have to do is, now the next thing which we'll be going to do is the number of bonds. Okay, so how many number of bonds it is forming? It is clear that it is bonded with 4 monovalent hydrogen, so it will be 4. Okay, so 4 minus 4 will be equal to 0. Okay, so 0 electron means 0 lone pair. Okay, so till now whatever structure we have done, remember that all have no lone pairs. Okay, and so the total number of electron pair will be bond pair plus lone pair. So it will be 4 plus 0, okay, which will be 4. So the number of electron pair is 4. Okay, so number of electron pair 4 means it is again tetrahedral. So it will be again the same geometry like methane. Okay, so which I can draw in something like this, NH4. Okay, so something like that. Okay, with a bond angle of 109 degree, which you can easily write that. Okay, if you want, you can show the positive charge also on ammonia. Okay, this is an ammonium ion. Okay, let me take some other examples. Okay, like let us go for some distorted geometries. Okay, so the distorted geometry, let us take some one of the simplest molecule which we have is H2O, water. What is the geometry of water molecule? Okay, if someone will ask you this, so what you will do first you will find out the number of valence electron on central atom, which is oxygen. So valence electron on oxygen. So valence electron on oxygen. So how many valence electron on oxygen? It's group 16, so 6, right? So number of bonds. In all the cases, I'm doing the very same thing. Okay, that's what, if you know for one, you know for all. Okay, so it is number of bond is 2. So now see, there is some valence electron left, and which is 4. 4 electrons are left. 4 electron means 2 lone pairs, is it not? So 2 electron will make 1 pair. So there are 4 electrons, so it will be 2 lone pairs. So what is the total number of electron pair? So bond pair plus lone pair. Bond pair is 2, lone pair is 2. So which is 4. So when we say 4, if I'll ask you what is the geometry, what will be your answer? Tetrahedral. So oxygen. So geometry, try to understand, be clear. Okay, I'm saying geometry is tetrahedral. So oxygen, the electronic arrangement will be like something like this only. Okay, no doubt in that. But the problem is, out of the 4 electron pair, 2 are lone pair. So let me make this lone pair. You can draw in this way, or you can make lobes also. Okay, that is up to you. So these are the 2 lone pairs which we have, and the other 2 will be hydrogen. Okay, now what will happen? Because these 2 are now actually the only bond pair which you have, and what I have told you, geometry is nothing but the arrangement of the electron density. Okay, the bond pair or the lone pair or the electron clouds. But remember that when we talk about shape, shape is decided by bond pair only. So remember that if anyone will ask you what is the geometry of water molecule, your answer is tetrahedral. Geometry is tetrahedral. What is the shape? Shape is not tetrahedral. Shape will be decided by this 2, and you can see it is forming a bent shape, or it can forming an angle, or it can actually, you can say it is a V shape also. Okay, it looks like V, right? Or it looks like an angle which is formed between the 2 bonds, or you can say a bent molecule. It's not linear, it's bent. So we call it bent shape. Okay, we call it sometimes angular. Okay, or sometimes we call it V-shaped also. So there are different actually names given to such shape. Okay, so that is how actually we get the shape now. So the shape and the geometry are different. So when it will be different? When the system or the molecule will have lone pairs. So those molecules which will have lone pair will have different geometry and shape, but those will have only bond pair, the geometry and shape will always be same. Okay, this is the perfect example to show that. And very important, what I have told you, if there will be lone pair, now the repulsion between the electron clouds, the bond pair and the lone pair and the lone pair and lone pair will be very high. As a result, if it would be a perfect tetrahedral, the bond angle should be 109. But remember that since there is a repulsion, okay, more repulsion from this electron cloud, since they are more free than the bond pair, so this lone pair will repel this bond pairs. Okay, as a result, the angle will now become less than 109. So it will shrink. And this angle in water molecule, if you try to find out, it is nearly to 104.5 degree. Okay, so it is 104.5 degree. So it is not 109. So why it has decreased so much? It is because of the lone pair bond pair repulsions. Okay, which is very, very high, right? As a result of which it will not have the regular angle, which is 109 degree. Okay, that is why we call it a distorted geometry. It is not a regular geometry. Regular tetrahedral must have 109. So this will be a distorted geometry, which actually we call as bent shape. Okay, so that is how we can understand, and that is how we can apply the VSEPR theory to determine the structure. Okay, let us go for some other shapes. Okay, like let us go for NH3. Okay, so how to get again same thing. First, valence electron, okay, on nitrogen. How many? 5. Number of bonds. So what is the number of bonds? It is 3. So 5 minus 3, 2. 2 means 2 electrons. So it is 1 lone pair. Once we are clear with that, then what we have to do next? Then bond pair plus lone pair, which will be equal to 2 plus, actually, sorry, it is 3. There are 3 bonds plus 1 lone pair. So it will be 4. Okay, so 4 means again tetrahedral. So geometry will be tetrahedral. Again, nitrogen. 1, 2, 3, 4. The basic geometry, tetrahedral. One of them is lone pair. So put one of them as lone pair. So the other 3 will be taken up by the bond pair, which is actually forming bond with hydrogen. Now again, what is the geometry of ammonia? Tetrahedral. What is the shape of ammonia? Not tetrahedral. Then you simply join this 3. When you join this 3, what you will get is now a pyramidal shape. You get something like this, right? It will be a pyramidal. Okay, so this is known as a pyramidal shape. You can clearly see also. That's why you don't have to by heart it that ammonia is pyramidal. You can look at it and you can say that it's a pyramid. Okay, so it is pyramidal shape. And again, the bond angle will not remain 109. That lone pair will repel that bond pair. As a result, what will happen is the bond pair, actually the bond angle over here again will shrink because of the repulsion and will go to nearly to 107 degree. Okay, so that is how we can actually understand that why the angle in the same molecule, some are tetrahedral, all are tetrahedral, the geometry, but some has different angle and the other have the angle of a regular tetrahedral. Okay, so again, the geometry of NH3 is nothing but, no doubt, it is nothing but the tetrahedral, but the shape will be pyramid. Okay, coming for the next, let us take some other molecules like, let us take some noble gas molecules like XeF2. Okay, xenon difluoride, right? Let us take this. Now, I don't have to tell you what is the valence electron on xenon. Valence electron on xenon is nothing but equal to 8, right? It is noble gas. So now, number of bonds. How many bonds it is forming? 2. 8 minus 2, 6. 6 electron. 6 electron means 3 lone pair, right? So number of bond pair plus lone pair now, total number of electron pair, number of bond pair is 2, lone pair is 3. So total 5. 5 means trigonal bipyramidal, right? So let us try to draw that xenon trigonal bipyramidal. So the basic geometry is something like this. So first the trigonal plane and then two pyramids, right? Now try to understand. Now there are three lone pairs. Now in this particular geometry, okay, you have to be very, very careful. As I have told you that there are two types of bond, the three which are forming the trigonal plane or are 120 degree to one another are called equatorials. The other two are axials. So you have to understand this. Now, if I want to put the lone pair repel more, right? So if I put them in axial, it is 90 degrees. So repulsion will be very high. But if I try to put them in equatorials, the repulsion compared to when you actually put them in axial will be less because they're 120 degree to one another. So very important point, whenever you have lone pair on this particular geometry, okay, which is nothing but trigonal bipyramidal, then you will always put lone pair on equatorial position, not on axials. So electron pair or the lone pair will always go to equatorial position, not on the axial position. So the three lone pair I'll put in equatorials. Okay, then the other two fluorine, it will go in the axial. So what is the geometry? Geometry is no doubt trigonal bipyramidal. What is the shape? Linear. You can see it's a line, right? So the shape is linear, geometry is trigonal bipyramidal. Okay, so very important and very much actually common. Okay, then coming for the next, let us take SF4. Okay, so SF4, again, valence electron on sulfur. How many? Group 16, 6. Okay, then the number of bonds, it is forming how many bonds with fluorine? Obviously 4. So 2 electron means 1 lone pair, is it not? So how many bond pairs you have? The number of bond pair which you have is nothing but 4. And how many lone pair? 1. So it will be 5. So you have 5 electron pair. Again, trigonal bipyramidal. So again, you draw the basic geometry. Okay. So the basic geometry is something like this. Now, the question is again, we have lone pair. Where this lone pair should go? We have one lone pair. One lone pair should go where? It should go in equatorial. So you put in equatorial position. Then you can put the rest of the fluorine in the other position. So what do we call this particular geometry? This particular geometry has a special name. We call it seesaw. Sorry, not the geometry, but the shape. So this particular shape is known as seesaw. Geometry, no doubt, is trigonal bipyramidal. Okay, a very important example actually for this particular shape. Okay, the seesaw. Now coming for the next. So let us try to take some other molecules, like let us take one anion, NH2 minus, amide ion. Okay, so again, number of valence electron on nitrogen, how many? 5. Now again, it has a negative charge, so plus 1, so will be equal to 6. Number of bonds, can you tell me? It is 2. 6 minus 2, 4. 4 means 4 electron means 2 lone pair. So how many bond pair and how many lone pair? Number of bonds 2, number of lone pair again 2. So total is 4. 4 means tetrahedral. Tetrahedral. Now what is the basic geometry? So nitrogen 1, 2, 3, 4. Then the 2 are lone pair. So 1, 2, 1, 2. And the other 2 are hydrogen. So what is the shape? Again, bent shape or angular or V shape. What is the geometry? Tetrahedral. Okay. So that is how actually you need to go for this particular VSEPR theory. Okay. Let me take one last example of sulfur dioxide. Okay, now this is quite tricky, that's why I'm trying to take it. So sulfur dioxide. Okay, so sulfur, now valence electron on sulfur, it is 6. Number of bonds. Now here, many students makes mistake. They write number of bonds 2. It's not 2. Remember that. No doubt, 2 oxygen is forming bond with sulfur, but oxygen is divalent. That part you have to be clear. So if it is divalent, oxygen will form double bonds. Is it not? So there is 2 oxygen. No doubt it will form 2 bonds, but 2 double bonds. So 2 into 2. Are you getting it? So how many electrons will be involved? 4. Although 2 bonds, 2 double bonds, but how many electrons are involved? 4 electrons. So it will be 6 minus 4, which will be 2. 2 electron, which will be 1 lone pair. Okay. So please be careful in this type of structures. Okay. Where there is divalent surrounding atom, like for oxygen. Okay. But remember that one of the basic postulate of VSEPR theory tells us that in VSEPR theory, double bond, triple bond, or single bond is always taken as a single bond only. Okay. So if you tell me that how many bond pair and how many lone pair, so bond pair plus lone pair. Now, bond pair, you should not write 4. Number of electron involved is 4. How many bond? 2 double bonds. Double bond, single bond, or triple bond are taken as single bond only. There is no such concept of double bond and triple bonds. Okay. So very important. If there is double bond also, 2 double bonds will be taken as 2 bond pairs. But the number of electron involved will be 4. Okay. So that's what this 2 into 2, what I am writing is this is 2 bond pair. Okay. Or 2 double bonds, and which involves actually 2 electrons. So 4. But when I write number of bond pairs, how many? 2, not 4. Okay. Plus 1 lone pair will be 3. So 3 means trigonal planar. So sulfur dioxide. So it will form something like this. Okay. And you will have 1 lone pair, which will be bend shape. Okay. So that is the basic geometry. So that is how actually we can go for the structural determination of various molecules. You can use this trick and get almost all molecules possible in a very, very easy way. Now, let me just give you a slight information about, small information about the hybridization. Okay. Now, whenever we talk about hybridization, since it is related, it will be very easy for you to get the hybridization also by using VSEPR theory. So you don't have to do so many topics. If you do one topic properly, you will cover all the topics. Whatever is the structure you are getting. Okay. So if you are getting the structure as linear, okay, remember that when we talk about structure, or what I am talking about is geometry, not shape. Okay. So be careful. So hybridization is decided by geometry, not by shape. Okay. So geometry, when geometry is linear, it will be SP hybridized. Please remember that. Whenever geometry, again, geometry is triangular planar. What is the hybridization? SP2. When it is tetrahedral, what is the geometry? SP3. When it is triangular or trigonal bipyramidal, okay, then what is the geometry? What is the hybridization? It is SP3D. Whenever it is octahedral, then we have SP3D2 or D2SP3. Okay, usually we call it SP3D2, but yes, when you are talking about coordination compounds, okay, then there is a slight change in this hybridization and the way we get it. Okay, so remember that whatever we are doing is for simple molecules, not for the coordination compounds. Okay, there we have to go for different approach. And lastly, if I have pentagonal bipyramidal, okay, so if I have this pentagonal bipyramidal, then what will be the hybridization? SP3D3. Please remember this. Okay, so this 3, this 6, if you can remember, along with the geometries, then all these topics will be done with a small trick. Okay, now whenever you do VSEPR theory, what you will do? you'll get the shape, you'll get the geometry, right? So if your geometry is linear, if they'll ask you what is the hybridization, you can find out it is SP. So if you get the geometry from VSEPR theory, you get the hybridization also. You just need to know the relationship between the geometry and the hybridization. Okay, so if I'll go with this, so if I put everything, number of electron pair 2, 3, 4, 5, 6, 7. So if I put all of this together, number of electron pair 2, geometry linear SP. Number of electron pair 3, trigonal planar sp2. Number of electron pair 4, tetrahedral sp3. Number of electron pair 5, triangular pyramidal sp3d. Number of electron pair 6, octahedral sp3d2. Number of electron pair 7, pentagonal bipyramidal sp3d3. Okay, and remember that, very important, whenever you determine the hybridization, don't go for the shape. Bent shape will not have any hybridization. Like if anyone will give you a slight example, a small example, H2O. What we found out for H2O? What is the geometry? Tetrahedral. Okay. So what will be the hybridization of water? It will be sp3. Please don't go for the shape. Okay. The hybridization is related to the geometry, not to the shape. So lone pair and bond pair both will decide the hybridization. But whenever we talk about shape, it will be decided only by bond pair. So whenever we talk about geometry and hybridization, both lone pair and bond pair. Whenever we talk about shape, it is always the bond pair. Like if I take NH2 minus amide ion, what is the geometry? Tetrahedral. Shape was bent. So what is the hybridization? sp3. Like if anyone will ask you, what is the hybridization of XeF2? What was the geometry we got it for? It was trigonal bipyramidal. So the hybridization will be sp3d. Although the shape is linear, don't say sp. Shape is linear. Geometry is sp3d. Okay. Like if anyone will ask you SF6, if you try to find out for SF6, you will get octahedral. Octahedral means sp3d2. If anyone will ask you SF4, which we have done, what was it? It was trigonal bipyramidal. Geometry, shape was seesaw, but geometry was SF4. So what is the hybridization? It is nothing but sp3d. Okay, so in this way, you can easily get what is the structure of different molecule. You can do almost all the molecules by this particular trick. You can find out the hybridization for all the molecules without using any equation, without using any mathematical expression, without using any any formulations, okay, without any theory. You can easily do that. You just need to understand the basics of VSEPR theory. You will be done from the shape, the geometry, and the hybridization. So that is how actually we work for, or how do we determine the various structure or the geometry or the shape or the hybridization of various molecules. So that is all about this particular video. Thank you, everyone. Do watch the other videos for the basic understanding for the other topics of chemistry. Okay, so thank you, everyone.